In this video, I would like to introduce you to the key concepts of power and how it can be applied to various problems. Power, which is denoted with a capital P, is really the rate of doing work. So when work is done, there is some energy transfer that occurs between the environment and the system or object. So power is the rate at which this energy transfers. So it's the rate of emission of energy. That's another way you could write it. Mathematically, on the AP formula sheet, power is equal to work divided by time. The capital W in the equation stands for work, measured in joules, and the delta T stands for the time, measured in seconds. So this brings us to the SI unit of power, which is equivalent to a joule per second, but a joule per second is denoted as a watt. So 1 joule per second is equivalent to 1 watt. You can write out the word watt, or you could rewrite this as simply capital W. But this can be kind of confusing for a lot of students because you have a capital W here for the symbol for watts, which is the units of power. But we also use the capital W in here in the formula to represent work. So don't confuse them. This is the watts, okay, which is the unit of power, and this capital W in the equation is just the symbol that we use for work. Now, in North America, you'll often see another type of power unit that comes from the old English units, and that's called the horsepower. This is abbreviated with HP, and 1 horsepower is equivalent to 746 watts. You see this kind of units, horsepowers, with electric motors and automobile engines, for example. In general, this power definition applies to all forms of energy. We'll use the same definition when we discuss electrical power, for example. We'll be talking about the rate at which electrical energy is being used. So whenever you're asked to say find the energy transfer rate, or the rate of emission of energy, we're really asking for what is the power. Because you could be, say, looking for any kind of energy transfer. It could be like a change in kinetic energy. It could be a change in gravitational potential energy, or it could be a change in electrical potential energy. So power can be written not only as, say, work over time, but since work is a change in energy, it can be rewritten as the change in energy divided by the time. This gives you what is known as the average power. Now, if the device is working at the same rate over that entire period, then it's finding the power for the entire period. But, often many devices are doing work, but they're not doing it at a constant rate. So even if the work is being done at different, rates, then you could still find the power at some specific instant in time. And so when you're finding the power at some special instant in time, that is called the instantaneous power, which is given by this equation. The average power would be equal to the force times the velocity times the angle, and this is the angle between the force vector and the velocity vector. Now this can be easily derived, by the way. Power is work over time, and if you recall, the definition for work is force times displacement times the cosine of the angle between the force and the displacement vector, and all of that is divided by time. If you look at the displacement divided by time, it's really just velocity. Remember, velocity is the displacement divided by time. So this can be rewritten as the force times the velocity times the cosine of the angle between these two vectors. Now, just a small, very quick little note for those of you guys in calculus, power is actually can be thought of as the derivative of the work function with respect to time. So it's dw by dt. But this is more of an aside. We will not see that in this course. This is only really for calculus-based physics courses. And I think there's another quick point I'd like to add in here. Since I've just introduced you to power and the associated units, SI units for power is in watts, which is the same thing as a joule per second, I think it would be fitting to introduce you to another unit of energy or work. We now know that a joule is equivalent to a Newton meter. So a joule is the same thing as a Newton times a meter. Well, something you're going to come to see, and this will come in more in the electricity unit, but I figured why not introduce it now. A kilowatt times hour, which is, we simply just call it a kilowatt hour, which is abbreviated as 1K, small k, capital W, times hour, right, is not what some people might mistakenly think because it has the word watt in there. They might think, oh, it's a power. And it's not actually a unit of power. It's actually a unit of energy. Let me show you what I mean. See, 1 kilowatt hour is really the power, well, not really the power, it's actually the energy that is being used, or the total work that is transferred during 1 hour, which is 3,600 seconds, and at a rate of 1 kilowatt, which is really 1,000 watts or 1,000 joules per second. So you could rewrite this, say this 1 kilowatt hour, you could write that as 1,000 watts, and you could write that 1 hour as 3,600 seconds. And a watt is really a joule per second. And you can see the seconds will cancel out, and you end up with 3,600,000 joules of energy. So whenever you see the units of kilowatt hours, you should be thinking a kilowatt hour is a unit of energy. And you should be able to, by the way, convert this into joules. So this is 3.6 times 10 to the power of 6 joules, which is really 3.6 megajoules. You might be wondering, why do we have these units? Well, they're convenient units that we use when you get charged for electricity that you use. Each month, your parents will get an electricity bill, and they're paying for the electrical energy that they've been using for their household. That energy is charged by the number of kilowatt hours that your household uses per month. Okay, go ahead and try the next two examples that deal with power.